Alright, well, here we are again for part 2 of lecture number 5 of ENGR 2302 Engineering Dynamics. And let's begin. Oh, we don't need that. Let's close that down. So I'm going to work here with, I want to begin covering the last bit of material from chapter 12 of the Beer Vector Mechanics book, and this is going to be angular momentum. So let's look at angular momentum of a particle. So angular momentum of a particle. Of a particle. Angular momentum of a particle. So here, if you consider an object in orbit, objects in orbit are a great example of particles with angular momentum, or things that can be considered particles. So a good example, good application of this are orbits. Of this is objects in orbit. So if you have an object, it may be orbiting in an elliptical orbit. So you have the greater mass here, and you had a certain plane here. So say this is, actually maybe I'll draw it a little bit bigger. Maybe you have the large radius r of the big object, and then maybe you have an axis here, an axis here. This is the big object, and you have a particle at some location here, A perhaps, and it has a velocity v naught. Here, v naught, and it will have a radius that changes over its elliptical orbit. So it'll have a radius that changes over its elliptical orbit. So it'll go from there, maybe over to here, and its velocity change, and its velocity will change, and its r will change. But at any given moment in time, it will have a radius, a small r. So that will be the actual coordinate at some time period that we can look at. That's the r of the smaller mass at any given time. And then also there is a theta here. So we'll have an r and a theta coordinate. Okay. So let's keep working. Let's work through the equations of this and see how this works. So if we look at a particle in polar coordinates, I want to look at this in polar coordinates now. Maybe we'll look at a particle with polar coordinates. So let's say I have the path P again in purple, or the path of a particle in purple, and a particle P, and there's a vector r from the center, and also a theta, r and theta. And then I'll have forces theta r and theta, fr and f theta. There is an f r on the object and an f theta. F theta, the tangent, the transverse, and radial components. So again, if I look at the forces in polar coordinates, we can see, so basically I'm trying to build my way up to angular momentum. Summation of forces in the r direction is equal to m ar is equal to m times r double dot minus r theta dot squared. Minus r theta dot squared. Summation of forces in the theta direction. Is equal to m a theta, which is equal to m r theta double dot plus 2 r dot theta dot. R dot theta dot. And this, maybe basically from this, we can derive the conservation of angular momentum. So we're going to call angular momentum H sub O. H sub O is mr squared theta dot. Mr squared theta dot. So if I looked at, so it's HO is mr squared theta dot. So I could look, if I multiply r times the summation of forces theta in the theta direction, this is equal to d dt. Ddt, this is an impulse momentum equation, mr squared theta dot. So just like if we remember from last time that the, if we remember from previous ones, we saw that force could be thought of as a rate of change in linear momentum. Remember that? We can think of it, force as a rate of change in linear momentum. We can also think of a angular force, a transverse force, as a rate of change in angular momentum if we multiply by the r by it. So r times the summation of forces in the transverse direction is essentially the rate of change of angular momentum. So if I work through this, I get that this is m, derivative with respect to time, will be r squared times theta double dot plus 2r r dot 2r r dot theta dot. Now you might ask, where did this come from? Where the heck did this come from? Ah, yes, the product rule. Yes, all I'm doing is the product rule. I'm taking the derivative of each of these with respect of this whole thing with respect to time, and since, well, mass isn't going to change with respect to time, but r and theta will, so I need to consider these both as independent variables, and I need to differentiate appropriately. Or if I then divide both of these by r, I can say the summation of forces in the theta direction is going to be equal to m r theta double dot. So basically I'm dividing by r across. R theta double dot plus 2r dot theta dot. Like so. So I'll keep working through this. Oh, and also this is equivalent to my kinetic diagram, or will be equal to my kinetic diagram of, well, I'll just draw the particle and save a little time. This is also equal to the kinetic diagram of for the particle P and AR and A theta. A theta here. Okay, so let us look more at the angular momentum of a particle. So angular momentum of a particle, we do actually have a slightly better way of getting this. Okay, so let's get this here. Let's see. So the angular momentum of a particle, continued. Let's actually define this a bit better. I think we've kind of worked our way up to this, but let's actually define it a bit more rigorously. Of a particle and it's going to be equal to, it's going to, first of all, just like linear momentum, it's going to be a vector. So H sub O, angular momentum, is going to be equal to R cross mv velocity vector, or mv vector. So again, one way to think of this, it is the moment of momentum. The moment of momentum. The moment of momentum, or the angular momentum. So if you remember back to statics class, and I ask you to find the moment of a force about a point, So the moment of a force about a point, so this is like statics review. You can see a parallel. Statics review. About a point, that looks really bad. About a point, well, the moment is equal to r cross f, right? The moment is equal to r cross f. And this is the same kind of thing, except instead of finding the moment of a force about a point, we are finding the moment of the linear momentum about a point. So we use the exact same method. mv is basically the linear momentum vector, right? And if we take the cross product of r and that, we will get the angular momentum. All right, so in other words, let's say we had something like this. If we have our x, y, and z, x, y, and z here. Oh, derp. Let me go back here. X, y, and z. If we have an r vector, and we're trying to find the moment about the origin here, if we have our r vector here, and we have a particle at P, let's say it's particle P here, and an mv vector here, well, the HO will be mutually perpendicular to each of these. Just like the cross product always gives you a mutually perpendicular vector, so the vector will always be perpendicular to both of these, but the axis would be acting through the origin here, because that's what we're taking moments about. And this would be your HO vector, something like this. And the book has a better illustration than I can draw on this with the hand sketch here, but that's the basic idea. And so, now that's the basic idea, but if, so again, not if, I should say, just to find out some other comments, HO is perpendicular to plane containing, is perpendicular to the plane containing R and MV and MV, and here, or HO is equal to, H sub O is equal to R MV sine of theta, where theta is the, actually sine of phi I'm going to use, sorry. Sine of phi, where phi is angle between R and V. Angle between R and V. Okay? Or this can also be said to be equal to R. So, oh, that's not right. R, or just simply M, Rm V theta. Rm V theta. When V theta, of course, is the tangential or the transverse velocity. And this is M R squared theta dot. M R squared theta dot. Okay? Then, let's see. What if I wanted to take the derivative of this with respect to time? So what if you take the derivative with respect to time, take derivative with respect to time, with respect to time, what do I get? Well, I can say from the previous one, if I take the derivative, H dot O, it will be R dot crossed into MV plus R crossed into MV dot, product rule again, equals V dot MV at mv, v dot mv plus r dot ma. However, this can be thought of as simply being equal to r. If this is just a sum of forces here, this can be equal to r crossed into the sum of forces, or better here, force vectors, or better yet, I can think of this as just the summation of moments.
Is that because v cross v is 0?
Yes. So then, because v cross v is 0, yes, that's true. Okay, so again, v cross v, this thing is going to go to 0. And then here, so think of the interpretation of this. This is what's really important. Basically, in order to get a change in the only thing that can produce a change in angular momentum, the only thing that can produce a change in angular momentum is a moment, is an outside moment. Is an outside moment. So, for instance, if you have a planet or an object that is in orbit around another, even if it's on a highly elliptical orbit like this, and then with the center here, while the force of gravity, the direction of it will continually change, it will always point right toward the center of the Earth, right? It's always going to be pointing right toward the center of the Earth. And it's always going to be perpendicular to the object's path at any given place in the orbit. So it's always going to be perpendicular to the object's path, and it's always going to point right towards the center of the orbit, or the center of the object. And what's important about this is if a force is pointing toward the axis, if a force is pointing towards the axis of rotation, that means it generates no moment. So what can you tell me about angular momentum across an orbit? Well, angular momentum across an orbit is definitely not 0. That would be falling like a rock. No, but the change in angular momentum over the course of an orbit is 0. The change in angular momentum over the course of an orbit is 0. It will remain constant across the entire orbit. So again, the sum of moments, or another way you can look at this is, the sum of moments about an axis or sum of torques, if you want to use that, will produce a change in angular momentum. Will produce a change in angular momentum. Okay, so let's move on to talk a bit about conservation of angular momentum. Okay? Oh, this here? Or the previous one? Okay. The sum of moments about an axis will produce a change in angular momentum. Okay, so conservation of angular momentum So, let me define something as a central force. Let me define the concept of a central force. Well, a central force is one that points toward the center. That makes sense. A force that points toward the center of motion. Towards the center of motion. Okay, so say we had a this would be an example of a central force here. And this here, this is the origin. Particle P, and there is a force pointing towards the origin. This is a central force, or as you could maybe also call it a centric force if you wanted to. So in this example, there is a force pointing from point F to the center of motion, and this is considered a central force. And because of this, it cannot produce any moment on the action, so on the object. So again, since line of action passes through about axis of rotation, passes through axis of rotation, through axis of rotation, axis of rotation, the sum of moments vector, which is going to be equal to the rate of change in the angular momentum, has to be equal to 0. And therefore, again, R cross m v naught, or sorry, m v vector, or the angular momentum is constant. So here is constant. So if you have any system where the only force acting on the particle or on the body is pointing toward the center of motion, there will be no change in the angular momentum. It may there may be a trade-off. It may trade height for velocity and vice versa, but the overall angular momentum will remain constant.
So this is just the force here is gravity of something going around a planet.
Exactly. In this example, it could be anything. Any kind of, it could be a ball going on a string. It could be I could be twirling a ball horizontally around my head or something on a string. You could have something like a centrifuge. You could have any number of things, but the purest example would definitely be something like an orbit. See, even if I was twirling a ball around a string, well, the problem is there's still gravity to consider, so it would always be pointing downward compared to our frame of reference. But the purest example of this would definitely be an object in motion or in orbit, an orbital motion. So in that kind of system now, even then, it's not a pure example because there's the gravity of multiple bodies. If you look at the moon, there's the gravity of the Earth affecting the moon, but the gravity of the sun also affects the moon, etc. Yada yada yada. But at least to certain limits, we can consider it a pure system like that. Again, so if we look at the vector here, the position vector and motion of a particle are in planes perpendicular to HO, and motion vector are in a plane perpendicular to HO, here, and magnitude of angular momentum, the magnitude of the angular momentum, well, if I draw it as not a vector, but as just an HO, just for the vector, or I could write this as HO magnitude sign, is going to be simply RMV sine phi. And this will be constant. So the overall magnitude of this, because if the vector is going to be constant, then the magnitude of it will also be constant. Or we could call it something like RO, which would be like an initial radius MVO sine phi O. And I'll draw this out, I think, actually. So say we had a particle that undergoes a change here. So originally it was here, and there was an RO here, and position O for here, and there was a MVO here, and then at some later time there is an R, and same particle, but maybe I'll call it P, position just P. And this would just be some generic MV, but a different thing, at a different angle perhaps. But anyway, the total magnitude will remain MVO sine phi O, sine phi O, or HO equals M R squared theta dot equals constant. Or another way to think of this is if I divide by mass, HO over mass equals R squared theta dot. Now I'll just call this H. This is like I'll just call this lowercase h. We do this a lot in many different engineering contexts. We say, we take a quantity like an extensive property that depends on mass, and we turn it to an intensive property by dividing by mass. And the extensive property here is total angular momentum, but if we divide by m, we get a lowercase h. We typically designate these with like capital and lowercase letters. So a capital letter is usually reserved for an extensive property, a lowercase letter for an intensive property. So this would be something like the total angular momentum for h naught, and lowercase h would be the angular momentum per unit mass, and this would be constant. Angular momentum per unit mass. Per unit mass. Now, let us look at this. Let's diagnose this, or let's try to, let's break this up a little bit. Oh, did you all got that? Okay. Oh, derp. Okay. Angular momentum per unit mass. So, R squared v dot equals h equals constant, or something like an orbit. So what does this mean? Well, R is going to be your radius, or your distance from the center.
You say phi dot, or you actually mean to say theta dot?
Did I mean to say theta dot?
You just switched partway through that.
Yeah, I may have switched that. Let me just go back here and see that. In that previous example, I used phi dot as just an example. I used phi here as an example, but generally I'm going to be using theta, okay? So h naught equals, let's see, a sine, let's see, what did I do here? Yeah, r naught mv naught sine phi naught. Yeah, that's good. But then this is more in general, or h naught equals this. So maybe this is at the starting location, phi naught being the starting location, etc. Okay? So phi would be your starting angle, and theta would be any angle, but it's somewhat arbitrary. Somewhat arbitrary. And this is your angular velocity. Something like radians per second. This would be something like just meters or kilometers, etc. Meters, kilometers, AU, whatever you want to use. Now, so here's the issue, or here, not the issue necessarily. We can see there's kind of a trade-off here. In other words, what I might say is r squared theta dot equals a constant k for any kind of system that is controlled by a centric force. So this applies to orbits. So in other words, if you have a very high rate in an orbit, you can trade one for another. And over the course of an orbit, you will trade one for another, but you can't get both. You can't get more of the both at the same time. So, say we have a object in a highly elliptical orbit around the Earth. This thing is not going to go around the Earth in uniform speed, or maybe this is a comet around the sun or something like that. Way out here, the radius is gigantic, right? A huge, huge, huge radius. And so what that's going to mean is if the radius is huge, the theta dot has to be very, very small. And so down here, though, when the radius is very small, the theta dot is going to be gigantic. It's going to be moving at an incredible rate, angular rate. In fact, it'll be moving at a very high velocity as well. And so we can actually see that at very high orbits, the orbital velocity actually declines.
Slingshotting around a planet.
That's exactly what they mean by slingshotting around the planet, although in that case you're actually using the planet to sort of gain momentum. you're sort of stealing some of the planet's momentum through a bit of the through an interaction of orbits. It's kind of like an analogy I've heard that's probably pretty good. Is like, imagine if you threw a tennis ball at the windscreen of an oncoming pickup truck. I don't know if you should do that. I think the pickup truck windshield would be fine, but I don't recommend trying it. You might have an angry truck driver chasing after you. So I don't recommend doing that, but it's the basic idea. If you're standing by the side of the road, I don't recommend doing this. Please do not actually attempt this. But if you're standing on the side of the road and you throw a rubber bouncy ball off the windshield of a passing truck, even though you might throw it at only, a certain number of miles per hour, if you throw it at, say, 30 miles an hour or something like that, if the truck's going by at 80, it might end up bouncing back at a far higher velocity than 30 miles an hour, won't it? And effectively, the momentum of the truck is unchanged, and you can do as conservation momentum and see what kind of change in momentum the bouncy ball would have, and you can, or the change in velocity the bouncy ball will have. So that might be interesting for an interesting calculation for y'all to do. But what else? So this is also why the further you are away from a planet, the higher the lower the angular velocity. Think about this. So I mentioned that that in low Earth orbit, an object might orbit every 40 minutes or something like that. So in low Earth orbit, you might orbit, say like low Earth orbit, LEO. Low Earth orbit, it might be even 40 minutes. So to find that angular velocity, you just divide 2 pi radians divided by 40 minutes. Much further out, much further out. Well, I don't really have time. I don't have room to draw much further out. So, and this is meant to be circular. I just can't draw circles. Perfectly circular orbit. You might have geostationary. So this might only be 120 miles up. Does anyone know off the top of their head the distance to geostationary orbit? It's 20,000 miles, 20,000 kilometers. It's on the order of it's on the order of 10 to 20,000 kilometers, if I remember correctly. I really should have looked that up prior. But geostationary orbit, how long does it take for a geostationary orbit to complete?
To go around the circle?
To go around the Earth, yeah.
24 hours.
Exactly 24 hours. Yes, that's the whole idea of a geostationary orbit. That is why, all of your kind of TV satellites are in geostationary orbit. You ever wonder why you can, think about who here has had at some point satellite TV? Come on, don't be shy, raise your hand. Where you probably had it at some point. Okay, you're all shy. Okay, so I saw a few hands of people who weren't shy and weren't scared, but okay. It's not a big thing, but anyway. Okay, so anyway, the point being, if you've seen a satellite dish, or you've all seen a satellite dish at some point, a ground residential satellite dish, do those things have motors on them? No, they don't have motors on them, but they're clearly directional antenna, right? They have a parabolic dish on them. So if the satellites move very quickly, right? They're going thousands of miles an hour, so shouldn't they need a motor to sort of track the bird through the sky and pin it on and really get their beam directly focused on that? Or, well, the satellite receiver isn't emitting a beam, but to really get their antenna focused on that direction, shouldn't they need that? Well, the answer is no, because it's in geostationary orbit. The whole idea of geostationary orbit is that they are at one particular elevation, at one particular height, the time. So again, but we said that, remember here, that r squared theta dot is equal to a constant. R squared theta dot is constant for an orbit. So what that means is, if you go far enough out, eventually, if r gets large enough, theta dot, what if you go out, so again, there's something special about this. What if you go out far enough that theta dot is exactly equal to 24 hours? So think about that. How would that work? Well, your orbit would take 1 hour to complete, and the Earth will take 1 hour to rotate. now you got something very good. See, from the point of view of someone on the ground, that satellite will sit at the same place in the sky all the time. So geostationary orbits are called geostationary, is because, and the reason for that is that compared to a spot, they stay directly above one spot on the equator at all times. And that's the real benefit of them. So you can park a satellite in that orbit, and then you just point your satellite dish at that particular orbit. You don't have to continually track a bunch of satellites. You don't need a big grid of satellites. You can cover a continent in a satellite signal with a single satellite. That can be very useful. Then, something with a higher orbit, something like the moon. Oh, and I went off this page. I can really not draw circles today. Something like the moon, Luna here. The time here, so this is again approximately 24 hours here. Well, actually exactly 24 hours. And something like the moon is approximately what? 1 month, 28 days, right? Approximately 28 days, or I can just say 1 month. Something at the distance of approximately the moon will have an orbital period of approximately 1 month. The moon, it takes approximately, so it's more like 28, 29 days, something like that, right? To go around the Earth. All right, that's kind of useful. Okay, so another thing, though, that we can look at is aerial velocity. Now, here's an interesting concept from orbits as well. Aerial velocity. This is a weird one. Aerial velocity is the amount of area swept up by an object's path in a period of time. And this was really one of the first discoveries about the orbits of the planets. Kepler didn't know anything about forces, he didn't know the law of gravitation, but he did come up with laws relating to the motion, purely the geometry. He didn't know anything about forces and gravitation, but his laws were purely about geometry, as we will see. An object's path in a certain time. So if you have an object here at O, an origin here at O, and then an object's path here, and an object's path. Let's say we have an object that goes from here to here, and let's say we have a original angle. Actually, let me put the origin down here. Put the origin down here. And then I have an original theta, or an original r here. And then let's, I had an original r here, and then I'll have a later r here. Although I'll consider it for the case, I'll just draw it kind of for the case of final, well, maybe this here. So let's say then the force, of course, acts toward the center here, force. F. And let's say we had initial theta and then a change in theta. Theta and then a d theta. D theta. And then let's say that we had a the length of this here, this path right here, would be r d theta. Okay? And what I'm after is the area swept by the orbit in a certain period of time. So maybe it would be this, I'll do that in yellow or something. It's this area all the way through here. Okay. So, and I'm going to call this area dA, the area swept. dA. So I can work through dA, I can work through the equations here, the geometry. dA equals 1/2 r squared d theta. And I can say dA dt, so I'm going to define area velocity. Areal velocity equals dA dt equals 1/2 r squared d theta dt. D theta dt equals 1/2 r squared phi double dot, or phi dot, or just 1/2 r squared phi dot. And again, so we know that since h equals 1/2 or equals r squared phi dot equals constant, we know that areal velocity, therefore areal velocity is also constant. Therefore areal velocity is also constant. The area swept by an orbit or an object will be constant throughout its orbit for any unit time. Is also constant. Okay, and from this, so let's also look at the law of gravitation. I just want to briefly mention this, although you've seen it in physics class, because we will be using this in some later examples. Let's see, so in case you don't remember the law of universal gravitation, we will go through that here. Let's see. So the law of universal gravitation, Newton's law of universal gravitation. Newton's law of universal gravitation. The big problem here is that the force is not going to remain constant as we sweep through an orbit. So this is what makes the analysis really difficult. Law of universal gravitation. So F is going to be equal to G_mm over r squared. Now I could say m1, m2, and that would be very true. Although usually this is configured for the case of one mass is much larger than the other, and G, of course, is the gravitational constant, which wasn't figured out till long after Newton was dead. The gravitational constant, and it is approximately 66.73 times 10 to the negative 12 meters cubed per kilogram second squared. Per kilogram second squared. Of course, Newton wouldn't know what any of these units were, so he might use something like 34.4. He might actually be using the centimeters slug system or something, but anyway, we could also, if I was using a pound system, I could say 34.4 times 10 to the negative 4, or 10 to the negative 9, foot to the fourth, divided by pound seconds to the fourth. Weird how that works out. And you might be surprised to see that I have length to the fourth and length to the third here, etc., etc. But where that comes from is simply the one is a mass system and one is a force-based system. And also it's important to realize that I have m, and I'll actually draw this one as a lot bigger than the other one, and m, small m, but these things are going to exert forces on each other, equal and opposite forces. Every force in the universe is always equal and opposite. So we have F and negative F vector. And this produces an interesting effect. See, if you look at the motion of, say, let's talk a bit about relative masses and the motions of orbits. Let's talk a bit about this. So in most of our analyses, we are going to deal with situations where one body absolutely dwarfs the other body. So most of the cases we're dealing with this kind of thing, where one body is just massively larger than another body, and this other one is basically just a particle compared to this other massive body. And here, we can actually treat this one, we can treat the larger one as really stationary. We can just treat the larger one as stationary. So it could be something like this. This thing's moving, but the other one really isn't. But if as the mass of this one increases relative to the other one, now in reality, this thing is actually moving. This is generating a force on this one, so that means it must be accelerating a tiny bit. Even the International Space Station going around the Earth is affecting the Earth's orbit or motion a very, 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 very tiny amount. But if you calculated the relative motion or the amount of motion that actually produces, as the space station goes around the Earth with a radius of the Earth's orbit or of its orbit around the Earth might go in a comparable circle. I don't know what we'd have to do the math on it, but it wouldn't surprise me if it was a fraction of the width of a proton or a fraction of the width of an atom or something tiny, nothing there. Yeah, just doing a very tiny thing like that. But as you get bigger and bigger, eventually, as this gets bigger relative to this, let's say you had something where you still had a dominant partner. But let's say you had the Pluto-Charon system, or really even the Earth-Moon system. The Moon is very large relative to the Earth. I mean, it's in terms of planets. In terms of planets and moons, it is huge. Moons are usually much, much smaller than their planets. The moon is actually, look at something like Mars. Venus has no moon. Mercury has no moon. Mars has a couple moons, but they are basically just asteroids, captured asteroids. Jupiter and Saturn and the other gas giants have several decent-sized moons, but they are absolutely dwarfed by the planets themselves. They're nothing. You could throw their whole moons into them and they wouldn't even notice. If you throw the moon into the Earth will notice. We would notice for a few seconds, but then we wouldn't notice much at all. But anyway, so for the primary and the secondary, the minor body would still be rotating like this, but then the major body would also be rotating, and it would have maybe a motion kind of like, maybe something kind of like this. Actually, it would help if I drew it through the center of the body, so maybe something like this. It would be a much smaller circle. The rotation would be much smaller, but if this thing's mass were significant relative to this, you could actually be able to notice this, and you could actually, if you could watch this from the North Pole of the things from a telescope, you could actually notice this. Or we could go all the way up to the extreme case. What if the two bodies are equal? What if we have a case of a true double planet, where each body is in motion, or is the same mass as the other one? What will happen here? What will happen here is that, again, this will experience a force here. This will experience a force here. And these things will just be a pair of dancing partners going around on the same orbit. They will likely be tidally locked to each other. Their same face will always point towards each other. And so this would be a double planet. And theoretically, you can have these. Nature. In nature, we would expect these to be fairly rare, but there may be actually some solar systems out there with. They'd be pretty rare, but there may actually be some solar systems out there deep in space that have double planets. And if they were both approximately the right size and the right orbit, you could actually have a really cool system. Imagine if you were on this planet, and imagine if both these planets, if their orbit around their star, happened to be in the habitable zone of that star. So imagine if you had two worlds that were both habitable and both had biospheres. Think about that for a second. That would be cool. So imagine looking up in the sky and seeing a second world. Imagine how that would affect the development of culture on that planet and things like that. Imagine how that would affect legends and everything of that nature. So that would be kind of cool. And so yes, theoretically you could have something like that. And that's
like electrons going in orbit. They're all the same mass.
Well, electrons aren't orbiting each other. That's the problem. So the question was, is that like electrons going around an orbit? The problem is they don't attract each other. So, but we'd have to talk about weird quantum things. But we're talking about in this class, Newton is correct and perfect forever. Einstein and Schrodinger are liars. And so this isn't science fiction physics. This is pure Newtonian physics. Einstein is lying, but anyway, not exactly. But what I should say for everything we're dealing with, we can solve it to any reasonable degree of accuracy with Newtonian mechanics only. So yes, you could have a double planet. And I would also like to mention something else in regard to orbits. Where is most of the solar system's angular momentum? Where is the solar system's angular momentum? Interesting. Where is the solar system's angular momentum? First of all, where is all its mass? Almost all of its mass. Yeah, almost all of its mass is in the sun. Almost all of its mass is, of course, in the sun. That's like 99.9 something percent of the entire solar system's mass is the sun. You could throw all the planets into the sun and they would never even notice it, right? Or the sun would never even bat an eye. But the angular momentum, actually very little of the solar system's angular momentum is in the sun itself. And the reason is because even though it has an incredible mass, all of that mass is very close to the center of mass of the solar system. So, there's actually two possibilities. I don't know the answer to this. I don't know if anyone knows the answer to this question right now. According to our current knowledge of the solar system, the current answer is Jupiter. And maybe not all of it, but the biggest chunk of it would be in Jupiter. Jupiter would dominate the angular momentum of the solar system simply because it has a tremendous mass, but it's also very, very far away from the sun. The other gas giants are farther away from the sun, so they have a higher, so they get more angular momentum that way, but they also have a much lower mass. Jupiter has much larger mass than the other gas giants. Jupiter is more mass than all the other planets put together, right? By many-fold. And so Jupiter holds, according to the traditional list of planets, Jupiter holds the bulk of the solar system's angular momentum. But I say current answer. Answer 5 years from now, who knows? Why would I say such a thing?
Does it just keep making planets into not planets?
No, it's not because they keep making planets into not planets, but even if we define Pluto as not a planet, that object, whatever we would call it, would still have the same angular momentum. It wouldn't change things. But there is an interesting thing that has been discussed, and that is that the sun's rotational angle does not necessarily line up directly with the average rotational angle of the planets. And also, there have been several papers that have come out recently based upon our knowledge of actually objects in the Kuiper belt, objects like Pluto, that they all have certain orbits based on the orbit. And you don't need to write this down. This is kind of just an interesting thing, the kind of thing you can do if you have a good knowledge of angular momentum and orbits, etc. Based on the orbits of detected Kuiper belt objects, there may be another planet out there, a big one. There may be another planet out there, another major planet. And it would be extremely far away. I mean, we're talking well beyond Jupiter in an orbital period that is thousands, perhaps 10,000 or more years long. And would be very, very far away. And so basically they have so you can, you can often infer the existence, you can sometimes infer the existence of one body from the orbits of known bodies. In fact, that's actually how we discovered Uranus and Neptune, where they saw that the orbits of Saturn and Jupiter were affected by certain things. And then later, based on those calculations, they knew where to point telescopes, and they later found the planets that were predicted. And so based on the orbits of these Kuiper Belt objects, there have been a couple major papers put out in the last year or two that, in very credible journals, that are predicting that there is a major body in our own solar system undiscovered in the year 2017.
Isn't that called Planet X?
People often refer to it as Planet X because people have looked for new planets for a long time, and so it's always been the kind of cool name for a mystery planet way out there. And it wouldn't be, incredibly interesting. You don't expect ET living out there, but probably just another ice ball out there. But it would still be kind of cool that there could be a big planet lurking in the far outer solar system, in our own solar system. Think about this. In the year 2017, we are discovering planets every day around other stars. And there could be a big planet in our own solar system that we don't even know about. Think about that. And so when I say big, what I've read, this may not be up to date, but the last I read, the predicted mass might be approximately 10 Earths. That is not a minor mass. That's a major thing. That's big. But the thing is, it would just be so far away that we haven't seen it yet. But it could still be in orbit around the sun and a really big honking rock out there, but totally undetected to us in the year 2017.
So it just has a really elongated orbit?
It would be very, well, the reason we haven't discovered it is a couple of reasons. If it exists, the reason we haven't discovered it, and it may not exist. It's possible this is just a fluke of the data. We don't know if this exists or not. That's the cool thing about science. You make predictions and you test them and you see what happens. That's that's the great thing about science. When it's the one field where you can ask a question and you can give an honest answer of I don't know, and that's a good thing. So most of the planets orbit in a central plane, right, called the ecliptic. Most of the planets orbit in a central plane along one plane called the ecliptic, right? But there are some orbits that are tilted slightly, like the orbit of Pluto is tilted a little bit. The orbit of Pluto is tilted slightly. That would be Pluto or something like that out there. But then this thing would be this would actually be one of the reasons we haven't caught it yet, is that if this thing exists according to the math, it would have a fairly high angle of inclination compared to the other bodies. And so if we have telescopes that are built to look at the other planets, well, that's one reason why we wouldn't see it, because we haven't been looking way up here. We've been looking here. And space is, the thing is, you might ask, well, we might wonder, how can you not find a planet? Well, planets are big, but space is bigger. Space is really, really, really big. You can lose an entire world out there and never even know it. So anyway, that's kind of cool. And you can go through the applications of this as well. And I'll give you a couple problems for your homework to work through the issues of angular momentum for orbits, etc., etc. I just like talking about space and orbits. Okay, so I think I'll finish up with a very simple explanation of Kepler's laws. Kepler's laws of planetary motion. I can't teach dynamics without covering these at least once. Of planetary motion. And again, these were described before Newton. So these are relationships that are purely described according to geometry. And this was laid out by Johann Kepler. So Kepler lived from Johann Kepler. He lived from 1571 to 1630. And basically, so he didn't know why the planets orbited in this way. He didn't know how what was driving the force of this. He simply said, look, I've taken these observations. Actually, another astronomer took the observations, and then he did the math on them to get these to determine these laws. But he determined the laws. But then Newton came along later and explained these in terms of a force called gravity. He said, oh, so again, Kepler said, I have noticed that orbits follow these laws, but I don't know why. Later, Newton came along and said, oh, the reason we have these laws is that the reason Kepler's laws make sense is that there is a force of attraction between all matter in the universe that is proportional to the product of the masses and inversely proportional to the distance between them. And so if you work through the math, this does explain Kepler's laws. But so again, these are geometric laws though. They don't have anything to do with force. They're purely geometric laws. Again, so these are Kepler's 3 laws. Each planet describes an ellipse, or each orbit of each planet describes an ellipse, with the sun located at one of its foci, at one foci, or one focus of that ellipse. The radial vector drawn from the sun to the planet, the sun to the planet, sweeps equal areas in equal time. Equal area in equal times. That's the conservation of angular or aerial velocity we saw earlier. Equal areas in equal times. And 3, the squares of the periodic times of the planets or basically the orbital period of the planets are proportional to the cubes of the semi-major axes of their orbits. And again, notice, each of these is purely a geometric relationship. It talks only about how the geometry of the orbit relates to time. It doesn't talk anything about masses. It doesn't talk anything about forces. These are the kind of things, even if you know nothing about mass or force or anything, if all you have is a telescope and an astrolabe, you can figure this out. And so all of these were determined just through years and years and years of carefully studying the motions of the planets in the sky and describing their orbits geometrically. All right, so I think that'll conclude my material for Chapter 12. I'll post a lecture for Thursday for the first part of Chapter 13. That will do it for today, and as always, thank you.